All right, strap in, everybody, because today we're going deep, deep into black holes.
But not just any deep dive.
Yeah, this isn't your everyday black hole chit-chat. We're talking about their chemistry.
The chemistry of black holes.
You got it.
It's fascinating
Yeah.
because, we think of these massive objects all about gravity, but what happens to matter, like, at a chemical level in these insane environments?
Right, it really pushes the boundaries. Like, imagine, I was just thinking about this the other day. You're at a cocktail party, right?
Yeah.
Someone brings up black holes, icebreaker, everyone's interested. But then you're like, well, what about the chemistry of black holes? It's not the first thing that pops into your head.
Right.
Mhm.
It's not the usual small talk.
It's not.
But that's what we're doing today. We're going to look at 5 key factoids
Okay?
to not only make you sound like a black hole whiz, but also start some really interesting conversations.
All right, I'm all for that. So factoid number 1, black hole physics 101.
Okay.
We all know black holes have this extreme gravity.
Right.
But help me, like, really grasp how it works?
Okay, so think of a star.
Okay,
Way bigger than our sun.
gotcha.
It runs out of fuel and it collapses under its own weight. All that mass squeezed into a tiny space. Boom, black hole. Now, the gravity of the super dense object is so strong it actually warps space-time around it.
Warp space-time.
Yeah.
Whoa, that sounds serious. So it's not just that things fall in. Space itself gets distorted.
Exactly. Like, imagine a bowling ball on a trampoline.
Okay, yeah.
You get that dip, right?
Yeah.
Black holes do the same thing, but to space-time. The heavier the black hole, the deeper the dip, the stronger the gravity.
So anything that gets too close to that dip, it's gone, right?
Well, that leads us to our second factoid, the event horizon.
Oh, here we go.
Imagine you're getting closer and closer to a black hole.
Okay.
Gravity's pulling you in faster and faster.
Oh.
You reach a point where the pull is so strong, nothing can escape.
Nothing.
Not even light.
Whoa.
That's the event horizon, point of no return.
So if light, the fastest thing out there, can't escape, we're definitely doomed.
Yep, pretty much. The event horizon, it's like a cosmic boundary. Once you cross it, there's no coming back. And it's all because the escape velocity, the speed you need to break free, exceeds the speed of light. And, well, that's the cosmic speed limit.
That's wild. So it's like the universe's ultimate do not enter sign.
Exactly. But let's keep going. Journey to the center, beyond the event horizon. Things get really crazy there.
Okay, I'm ready.
We find the singularity.
The singularity, I've heard the term, but what does it actually mean?
Okay, imagine all the matter that fell into the black hole, all crushed into an infinitely small point.
Infinitely small.
Infinitely dense.
Okay,
That's the singularity.
okay.
Laws of physics as we know them.
Yeah.
They don't work there.
Wait, so infinite density. How is that even possible? It just doesn't compute.
That's the thing with black holes. They really push the limits of what we understand. We don't truly get what happens at the singularity. It's like the point where our current theories just
Stop working.
Yeah.
So it's a big question mark in the middle of a black hole.
Basically, yeah, this point of mystery. But it's there.
It's there somewhere. Okay, so intense gravity, check. Inescapable event horizon, check.
Yeah.
Mind-bending singularity, check. But I heard black holes aren't actually totally black. There's this thing called Hawking radiation, right?
Yeah, you got it. Stephen Hawking, he proposed this incredible idea
Okay.
that black holes, they're not completely dark.
Really?
They actually give off this faint radiation due to quantum stuff near the event horizon.
Okay, quantum stuff near the event horizon. Layman's terms, please. How can anything escape a black hole? Even radiation.
All right, so picture empty space right near the event horizon.
Okay.
Now, it's not truly empty. Quantum mechanics says these pairs of particles, they pop in and out of existence.
Okay.
And sometimes, near a black hole, one particle falls in, the other escapes. And it takes a little bit of the black hole's energy with it.
So they're like stealing energy from the black hole. That's amazing.
Yeah, and over, like, ridiculous amounts of time, this process can actually make the black hole evaporate.
Black holes can evaporate. That's a new one. So we've got intense gravity, the inescapable event horizon, the mind-boggling singularity, and now evaporating black holes. What's next on our black hole hit list?
Now we get to the really uncharted territory.
Yeah. Oh, boy.
Quantum gravity.
Okay.
So black holes, we know gravity's off the charts there. Space and time are warped.
Yeah.
It makes you wonder what happens to chemistry under those conditions.
Chemistry in a black hole. That's a new one.
Right. It's a whole new frontier. Our usual chemistry, it's based on quantum mechanics, right?
Right.
Atoms and molecules, that kind of thing. But those laws, they don't really work with our understanding of gravity.
So you're saying our chemistry textbooks are useless in a black hole?
Pretty much, yeah. We need a whole new framework to figure out how chemistry even works in those crazy conditions. That's where quantum gravity comes in.
Okay.
It tries to put together quantum mechanics and general relativity. It wants a single theory that can explain the universe at all levels.
So we need like a whole new rule book for black hole
Yeah,
chemistry.
exactly. It's like, imagine trying to play a game, but the rules are completely different. The field's all warped and weird. That's a black hole.
Okay, my brain is officially fried. But before we get lost in the theoretical jungle, let's take a breather. We'll
Yeah,
come back and unpack this whole quantum gravity thing. I have a feeling we've only just dipped our toes in.
definitely.
There's more to come.
Welcome back to this deep dive.
Oh, my brain's still hurting from that last factoid.
Quantum gravity, right?
It sounds like so sci-fi.
Yeah, it kind of does, but it's a real thing, and we need it if we want to understand what's happening to matter, like at the chemical level inside a black hole.
Okay, so our regular chemistry, it doesn't really work in these crazy environments, right?
Not so much, no.
Can you, like, give me an example? What would happen to just a plain atom if it got sucked in?
Okay, so picture a hydrogen atom, simplest one there is, right?
Right, one proton, one electron.
Exactly. Normally, that electron orbits the proton, nice and safe distance, electromagnetism, all that.
Right, right.
But inside a black hole, gravity, that's the big boss.
So it just overpowers everything else holding the atom together.
Pretty much, yeah. As the atom gets closer to the singularity, all that gravity starts squeezing it, pushes the electron closer and closer to the proton.
Like a cosmic crush.
Haha, yeah. So what happens then? Does it just implode? Well, we don't know for sure, but this is where things get really interesting.
Okay, tell me more.
At some point, the electron, it might get forced to merge with the proton, forms a neutron. It's called inverse data decay. We actually see this in some extreme places, like neutron stars.
So the atom, it changes into a different particle completely.
Exactly. And if the gravity's strong enough, even neutrons, they might break down further, release their quarks.
We're talking like fundamental breakdown of matter.
Yeah, like the fabric of space-time is getting ripped apart.
Whoa, okay, so atoms getting squished, electrons and protons merging, quarks flying around. It's like a subatomic demolition derby in there.
Haha, great way to put it. And it's not just atoms. Molecules, those building blocks of everything, they get hit hard too.
Okay, so like what happens to a water molecule? Just gets ripped apart.
Well, first, the bonds holding those hydrogen and oxygen atoms, they might actually get stronger under all that pressure.
Really?
Yeah, but as you get closer to singularity, even those bonds, they snap. You just end up with a soup of subatomic particles.
The ultimate cosmic smoothie?
Yeah, something like that. And remember, we're just speculating here, using what we know to guess what might happen. The reality could be way weirder.
It's already pretty weird. I never thought about black holes like this. Like they're places where chemistry goes haywire.
It's one of the things that makes them so fascinating, right? They challenge everything we think we know.
So we've talked about how black holes mess with matter at the atomic level, but what are the big picture? Do black holes affect the chemistry of the entire universe?
That's a great question, and it leads us to another really cool aspect of black hole chemistry.
Lay it on me.
They're not just these cosmic vacuum cleaners sucking everything up and destroying it. Black holes, they actually help create and spread elements throughout the universe.
Really? I thought stars did most of that.
Yeah, stars are the main element factories, but black holes play a part too. Like when a huge star collapses into a black hole, it can cause a supernova.
Supernova, yeah, those are huge explosions.
Massive explosions, tons of energy, and that energy creates this like cauldron where lighter elements get fused together into heavier ones. Old, silver, platinum, all that good stuff.
So the jewelry we wear, it could be thanks to a black hole.
It's possible, yeah.
That's pretty cool. So how else do black holes contribute?
Well, they power some of the most energetic stuff in the universe, like quasars and active galactic nuclei.
Refresh my memory, those are.
They're basically supermassive black holes at the center of galaxies, and they're actively eating matter.
Oh, right, right. And as they eat, they release huge amounts of energy.
Exactly. That energy, it heats up the gas and dust around them, creates environments where you can have these huge-scale chemical reactions.
So it's like black holes create these cosmic furnaces where new elements are being forged and all sorts of chemical stuff is happening.
Yeah, that's a great analogy. And these processes, they really shape how galaxies evolve, how stars and planets form, their chemical composition, all of it.
Wow, so black holes, they're affecting everything from the tiniest atom to the largest galaxy.
Exactly. They're not just these weird gravity-bending objects. They're powerful engines driving the universe's evolution. And they shape the elements that make up, well, everything.
This is blowing my mind. Black holes, they're not what I thought they were.
That's what science does, right? It changes our perspective, shows how everything's connected.
So what other wild stuff awaits us in this deep dive? What's next?
Next, we're going even deeper into the theoretical rabbit hole. We're going to talk about wormholes, those tunnels through space-time that could connect different parts of the universe.
Yeah, now we're talking science fiction.
Maybe, but who knows? Black holes might be the key to interstellar travel. We'll see.
Back again for more black hole craziness.
It's been a wild ride, hasn't it? Crushing gravity, evaporating black holes. We even talked about, like, how chemistry gets totally flipped on its head in these extreme environments.
Yeah, my brain's still catching up. And now we're going to talk about wormholes. This feels like we've gone full sci-fi.
Well, the idea of wormholes is definitely captivating. These tunnels through space-time, they could connect like super far off points in the universe.
So like a shortcut through space.
Yeah, imagine going from one galaxy to another, just like that.
Okay, that's pretty awesome. But how do wormholes tie into black holes? Do black holes make wormholes?
That's one idea. Some physicists think that with all that crazy gravity black holes have, they warp space-time so much that they could create these tunnels.
So you're saying if we could, I don't know, harness a black hole somehow, we could make a wormhole and travel the universe?
Maybe, in theory. But there are some big ifs here. First, we've never actually seen a wormhole. They're just theoretical for now.
Right, right.
And second, even if they do exist, traveling through one, that's a whole other can of worms.
So no hopping in a spaceship and zipping through a shortcut?
Not that easy. We're talking about places where the laws of physics, they might not even work anymore. Massive gravity, exotic matter, things we barely understand.
Okay, so interstellar travel via wormhole is still a pipe dream.
Probably, yeah. But it's still pretty amazing to think about.
Definitely. Okay, so we've talked about the crazy stuff happening inside black holes. But what about the big picture? What's their role in the universe overall?
Another good question. Black holes, they're more than just these weird objects. They're really important for how the universe evolves and, how it's structured.
Can you give me an example? How do they affect things on such a large scale?
Like we talked about before, black holes, they're crucial for how galaxies form and change over time. Their gravity, it holds galaxies together, affects how stars orbit.
So like the cosmic glue that keeps everything from flying apart.
Exactly. And when they devour matter, they release all this energy, which can heat things up and even trigger the birth of new stars.
So they destroy things, but they also create things. That's kind of a paradox.
Yeah, it shows how everything in the universe is connected. Black holes, they're not just off on their own doing their own thing. They're part of this cosmic dance that shapes everything.
This whole deep dive, it's really changed how I see black holes.
That's what's great about science, isn't it? It keeps us guessing.
I'm definitely left with a sense of awe as the universe is so vast and mysterious.
And that's the beauty of it, right? Always something new to discover. Who knows what we'll find out about black holes next?
Well, on that note, I think it's time to wrap up our black hole chemistry adventure.
It's been fun, hasn't it? We hope you learned some cool stuff about these mysterious objects.
Until next time, keep looking up at the stars, everyone. And remember, out there, amidst all that beauty, there are these incredible things, bending reality and challenging everything we think we know.
Keep exploring, keep asking questions, and never lose that wonder about the cosmos.